chloric acid produce sodium chloride and water. This reaction is called non-reversible reaction, in which it takes place in one direction only. When the limiting reactant in this reaction completely consumed, reaction will stop and go to completion. However, there are also reactions which do not go to completion, but it will reach equilibrium. These reactions are called reversible reaction. A reversible arrow is used to represent this kind of reaction. This reversible arrow indicates the reaction which takes place in both directions, forward and also reverse. The forward arrow shows the reactants forming products. Meanwhile, for the reverse arrow, it indicates that the product producing reactants. The curve of concentration against time shows the changes in the concentrations of both reactants and product with time. Concentration of reactant A tend to decrease with time, and the concentrations of product B tend to increase with time. After time T1, the concentration for both reactants and product remain unchanged. This indicates that the reaction already reached equilibrium. As time goes by, for every molecules of reactants that gets converted to products, a molecules of products will get converted back to reactants at the same time. This is what we call equilibrium, a state in which there are no observable changes as time goes by. By referring to the curve of concentration against time, the equilibrium after time T1 is known as dynamic equilibrium, which means at this state, the reaction does not stop and it will continuously react. The rate of forward will be equal to the rate of reverse, and no net changes can be observed to the concentration for both reactants and products. By using these general equations of reversible reaction, the law of mass action, or known as the law of chemical equilibrium, can be transformed into an expression. At equilibrium, the ratio of the concentrations of the products C and D that raise to their respective stoichiometric coefficient over the concentrations of the reactants A and B that raise to their respective stoichiometric coefficient is a constant at constant temperature, which means will be equal to K, an equilibrium constant. By applying the law of mass action to this example of reversible equation, we can have, at equilibrium, the concentrations of NO2 to the power of 2 over the concentrations of N2O4 to the power of 1, or we just can simply write the concentration of N2O4, and all of these will be equal to K. When this system reaches equilibrium, the forward and reverse rate will be equal and the concentration for both reactants and product will remain constant. By referring to the same example of reversible reaction, we can have three different kinds of curve concentration against time. The first one is when the reaction starts with a product L2. The next one is when the reaction starts with the reactant of N2O4. And the last one is when both reactants and products start together. All of this graph shows the part at which the concentration for both NO2 and N2O4 remain constant. This indicates that the reaction already reached equilibrium. At this state also, the rate of forward and reverse reaction will be equal to